Welcome to Hired in IT. Imagine a team launches a server for a small application. Traffic is light, but the instance runs day and night. 30 days later, the bill arrives. Not because the application was busy, but because the server stayed on. That is the EC2 versus Lambda decision in one picture. EC2 gives you a virtual machine that runs until you stop it. Lambda runs code in response to events. The right choice depends on the workload, how long it runs, how often it runs, how much control it needs, and what you are willing to operate. Lambda is not automatically better because it is serverless, and EC2 is not automatically wrong because it is a server. A tiny daily job does not need an always-on instance. A long-running service with persistent connections is not a natural fit for a short-lived function. Most expensive AWS mistakes happen when teams choose the service first and inspect the workload second. In this video, we will use a simple filter to decide between EC2 and Lambda: traffic shape, execution time, and required control. By the end of this video, you will be able to explain the core mental model. EC2 is a virtual machine you operate. Lambda is event-driven code that runs on demand. You will also run every workload through 3 questions. Is the work steady or event-driven? Does it need deep operating system or hardware control? And can each unit of work finish within the Lambda execution model? Along the way, we will decode the AWS names as we use them. An AMI is the image an EC2 instance boots from. S3 is object storage. CloudFront is a content delivery network. API Gateway receives and manages API requests, and DynamoDB is a managed NoSQL database. EC2 is a server you operate. You choose the base image it boots from, pick a size, set up access controls, and attach storage. After it launches, you still patch the operating system and watch CPU and logs. And you pay for the time it runs, even when it is mostly idle. Lambda changes the operating model. Instead of provisioning a general-purpose server and keeping it running while it waits for work, you upload code and connect that code to an event. That event might be an object uploaded to Amazon S3, a message arriving in a queue, an HTTP request, a database change, or a scheduled event. When the event arrives, Lambda invokes your function and provides an execution environment where your code can run. For a standard on-demand Lambda function, billing is based primarily on the number of requests and the execution duration used to process them. When nothing invokes the function, there is no request or execution duration charge. But here's an important detail. That doesn't mean the Lambda execution environment instantly disappears after every request. AWS may reuse an existing execution environment for later invocations. Your application should never depend on that reuse, but it can improve performance. And serverless doesn't mean the entire architecture becomes free when the function is idle. Provisioned concurrency and supporting services such as API Gateway, storage, databases, logging, and networking can still generate charges. The important difference is the operating model. With EC2, you're keeping a general-purpose virtual machine available. With standard on-demand Lambda, you're paying primarily when your function is actually invoked and executing. Remember, EC2 keeps the server available. Lambda runs code when work arrives. Lock in this frame because the rest of the video uses it. EC2 is a virtual machine you provision and operate. It runs until you stop or terminate it, and you pay for the compute time while it runs. You choose the operating system, instance type, network configuration, and attach storage. Lambda is event-driven compute. AWS manages the execution environment, and a standard on-demand function runs only when invoked. Billing is based primarily on requests and execution duration. EC2 can use durable EBS volumes for persistent storage, although local instance store data is temporary. Lambda has temporary local storage that can be useful as a cache, but durable application data belongs in services such as S3 or DynamoDB. Quick recall check. You leave a running EC2 instance and a standard on-demand Lambda function completely idle for a full weekend. Which one still has compute charges? The running EC2 instance. It remains allocated and billed for the time it runs, even if CPU utilization is near zero. The standard on-demand Lambda function has no request or execution duration charge when nothing invokes it. Remember the caveat. Provisioned concurrency and supporting AWS services can still create charges. Here is a common Lambda pattern. An object lands in an S3 source bucket, or in an incoming prefix. That upload event invokes Lambda. The function resizes the image, then writes the result to a separate destination bucket or a processed prefix that does not match the trigger. That separation matters. If a function writes output to the same matching S3 location that invokes it, the output can trigger the function again and create a recursive loop. Notice the mental shift. There is no always-on server waiting for an upload. The event invokes the function only when work arrives. Before you choose either service, run 4 questions. Is the workload steady or bursty? Is it long-running or short? Do you need full OS control, or is a managed runtime fine? And do you hold persistent connections like a chat server, or handle request-response calls? In practice, steady, long-running, full control, and persistent connection workloads lean toward EC2. Bursty, short, managed runtime, and request-response workloads lean toward Lambda. Treat these as heuristics, not guaranteed rules, and check current AWS docs for any workload you are not sure about. In the AWS console, open Lambda and choose Create function. Name it resize image, select a currently supported Python runtime, and create a basic execution role that allows the function to write logs to CloudWatch. Run a sample test event and inspect the response and logs. For this first function, you do not choose an AMI, create a key pair, or patch an operating system. If the application later needs private network access or permissions to other AWS services, configure those deliberately instead of adding them by default. Now let's compare one of the biggest differences between EC2 and Lambda: how long the workload can run. A standard Lambda function currently has a maximum execution duration of 15 minutes for a single invocation. That's 900 seconds. EC2 doesn't use that same per-invocation execution model. An EC2 instance can continue running until it is stopped, terminated, interrupted, fails, or is otherwise affected by the infrastructure or purchasing model you're using. That's why EC2 is a more natural fit for workloads that require long-running processes, persistent services, continuous background processing, or software that needs a host environment available for extended periods. There's another difference: startup behavior. Lambda may need to create a new execution environment when a function is invoked. That can introduce a cold start. A running EC2 instance already has its operating system and application environment running. And finally, control. EC2 gives you operating system level control. Lambda does not give you direct access to the underlying host, so don't memorize this as Lambda equals 15 minutes, EC2 equals unlimited. Remember the actual architecture difference. Lambda processes individual invocations inside a managed execution model. EC2 gives you a persistent virtual machine environment that you operate. Quick checkpoint. What is the current maximum execution duration for one standard Lambda function invocation? 15 minutes, or 900 seconds. Now here's the more important architecture question. What happens if one indivisible unit of work must execute continuously for longer than 15 minutes? It cannot fit inside a single standard Lambda function invocation. At that point, evaluate another execution model. Depending on the workload, that might include EC2, containers, AWS batch, or another appropriate AWS service. Some larger workflows can also be redesigned into smaller steps and coordinated across multiple invocations. But don't break a workload into functions simply to force it into Lambda. Start with the business and technical requirements. Then ask, can this work naturally be divided into focused, event-driven units? If yes, Lambda may still be part of the architecture. If the work truly requires one continuous execution lasting longer than 15 minutes, use a compute model designed for that requirement. So remember, 15 minutes is the limit for one standard Lambda invocation, not necessarily the duration of the entire business workflow. Now look at a common serverless version of a 3-tier application. CloudFront and S3 can serve the front end. When the browser makes an API call, API Gateway invokes a Lambda function. That function reads or writes data in DynamoDB, then returns a response through the API layer. This design can remove much of the server, instance, and load balancer management. But it does not remove architecture work. You still design authentication, authorization, data access, monitoring, error handling, and, in some workloads, networking and VPC connectivity. The key trade-off is simple. You give up direct host access and long-running execution in exchange for a more managed, event-driven compute model. Here's one of the biggest operational differences that doesn't always appear on an architecture diagram. With EC2, you have a virtual machine. If something goes wrong, one troubleshooting option may be to connect to the host and investigate directly. You can inspect processes, files, services, operating system logs, network configuration, memory, disk usage, and the application running on that machine. Lambda changes that troubleshooting model. There is no customer-managed server for you to SSH into. Instead, your investigation depends much more heavily on application logs, metrics, structured logging, tracing, and the context captured around each invocation. Amazon CloudWatch becomes one of your primary tools for understanding what the function did and why it failed. This leads to an important serverless lesson. Serverless doesn't remove infrastructure. It removes your direct access to much of the underlying infrastructure. That means observability becomes even more important. If your application doesn't produce useful logs, metrics, and traces, troubleshooting a distributed serverless application can become difficult very quickly. So when you're learning Lambda, don't only learn how to write the function. Learn how to observe it. Because in serverless architecture, you troubleshoot through telemetry, not by logging into the server. Here is the key billing contrast. With a running EC2 instance, compute charges continue while the instance runs, including during idle time. With a standard on-demand Lambda function, billing is based primarily on requests and execution duration. That makes Lambda attractive for intermittent, short-lived work. It does not make Lambda automatically cheaper for every workload. Provisioned concurrency, related services, data transfer, storage, and inefficient function design can all affect the final architecture cost. Use the chart as a starting point, then calculate the cost of your own workload with its actual traffic, duration, memory settings, availability requirements, and connected services. Here's a mistake teams sometimes make. They choose the compute service first and inspect the workload second. One team has a steady application workload. They move it to Lambda because serverless feels modern. Then they look at the architecture, latency, or cost, and conclude, serverless was a mistake. Another team has a tiny automation job that runs for 20 seconds once a day. They deploy an EC2 instance and leave it running 24 hours a day. Now they're maintaining and paying for a virtual machine that spends most of its time waiting. Neither example proves that Lambda is expensive. Neither proves that EC2 is inefficient. They demonstrate the same architecture mistake. The compute model wasn't matched to the workload. Before choosing EC2 or Lambda, ask, how often does the work run? How long does each unit of work take? Does the application need a persistent process? Does it need operating system control? Does it maintain long-lived connections? What happens when there is no traffic? What does scaling look like? And what will the complete architecture cost? Don't choose Lambda because it's serverless. Don't choose EC2 because it's familiar. Choose the execution model that matches the work. When you trade a virtual machine for a serverless function, you lose direct host access. What becomes your first debugging window? CloudWatch logs. For production systems, add metrics and distributed traces as well. But logs are often the first place you see the event, the function output, an error message, and the duration of the invocation. Let's turn everything we've learned into a simple decision framework. Run the workload through 3 filters. Filter 1. Is the work naturally event-driven? Does something happen that should trigger a focused piece of code? An object arrives. A message appears. An API request comes in. A scheduled event fires. If the work is naturally event-driven and can be broken into focused units, Lambda may be a strong candidate. If the workload is a continuously running service or persistent process, evaluate EC2, containers, or another compute model. Filter 2. How much control does the workload require? Do you need operating system access, custom system software, specialized host configuration, specific hardware, a persistent host environment? If yes, EC2 or an appropriate container platform is usually a more natural starting point. If a managed runtime works, Lambda becomes more attractive. Filter 3. Does the execution model fit? Can each unit of work finish within the standard Lambda invocation limit? Can the function operate without depending on one persistent server? Can durable state live outside the function? Does the compute itself need to maintain a long-lived connection or persistent process? If the workload requires one continuous execution longer than the Lambda limit, or the compute itself must remain persistently connected, compare EC2 or container services such as ECS or Fargate. But remember, these are decision filters, not automatic rules. A serverless architecture can still participate in systems involving web sockets, streaming, long-running business workflows, and persistent data. The question is where those responsibilities live. So after these 3 filters, validate performance, reliability, security, operations, and total cost. That's how architects choose compute. Start with the workload. Then choose the execution model. Imagine 2 jobs. The first checks a folder once a day, processes a file for 20 seconds, and then stops. Keeping an EC2 instance running all day for that job creates a lot of idle compute time. Lambda is a strong candidate. The second runs a service continuously, handles long-lived connections, and needs full control of the environment. Lambda is not designed for that model. EC2 or containers are more natural options. The point is not that one service always wins. The point is to compare the duration of the work with the duration of the infrastructure you are paying for. The console is useful for learning, but real automation often happens through the CLI or infrastructure as code. A typical Lambda creation command includes a function name, a supported runtime, code package details, and an IAM execution role. The runtime tells AWS which language environment to load. The execution role gives the function permission to call AWS services without storing long-term access keys in the code. That does not eliminate all configuration. You still choose memory, timeout, permissions, logging, network settings when needed, and the event source that invokes the function. The important shift is operational. You define the function and its requirements, instead of building and maintaining a full virtual machine. The trap is not just the 15-minute timeout. It is assuming a Lambda function becomes a general-purpose server once it is running. A batch job that needs hours of continuous processing does not fit a single standard Lambda invocation. A workload that must keep a client connection open also needs a different execution model. When you see long-running work, persistent processes, specialized host requirements, or always-on connections, compare EC2 or container services such as ECS or Fargate. Lambda is excellent for focused, event-driven units of work. It is not a universal server replacement. Quick decision checkpoint. Your application requires custom system software, operating system tuning, direct control over the host environment, and a process that must remain running continuously. Which is the more natural starting point? EC2 or Lambda? EC2. EC2 gives you control over the operating system and the virtual machine environment. You can install system-level software, configure the OS, manage services, attach persistent storage, and keep processes running continuously. Lambda intentionally removes much of that server management responsibility. That's one of its biggest advantages. But removing server management also removes direct server control. So don't think EC2 is old and Lambda is modern. Think EC2 gives me a server environment I control. Lambda gives me managed event-driven execution. If the workload genuinely needs the server, choose the service that gives you the server. Cold starts happen when Lambda needs a new execution environment and must initialize the runtime and your function's setup code before the handler runs. Provisioned concurrency keeps a chosen number of execution environments pre-initialized and ready to receive requests. It is designed for latency-sensitive workloads, especially interactive APIs with predictable demand. That improvement has a cost. You pay for the provisioned environments while they are allocated, even when they are not processing requests. Use it selectively. Measure the user-facing latency first, then apply provisioned concurrency to the specific functions and versions where the benefit justifies the cost. Here's something that gets lost in EC2 versus Lambda comparisons. You don't have to choose one service for the entire application. Many architectures use both. Imagine an application with a steady backend service. That core workload might run on EC2. Now imagine users upload images. Instead of making the EC2 application process every image, the upload can trigger a Lambda function. The function performs the image processing task and exits. Another Lambda function might handle a scheduled cleanup job. Another might react to an event from a queue. Meanwhile, the long-running application remains on EC2. That's a hybrid compute architecture. Each part of the application uses the execution model that fits its workload. You can also centralize much of your observability. EC2 applications and Lambda functions can send logs and metrics to Amazon CloudWatch, giving you a shared observability platform across the architecture. Depending on the application, you may also use distributed tracing, load balancer logs, network telemetry, application performance monitoring, and other diagnostic sources. So CloudWatch isn't necessarily the only place you troubleshoot. It's part of a broader observability strategy. The larger lesson is, architecture isn't EC2 versus Lambda. It's which parts of this application belong on which compute model. Sometimes the best answer is both. Cold starts are real, but they do not mean serverless is broken. Start with the basics. Keep dependencies and initialization work focused, because package size and code that runs before the handler can affect startup time. Reuse clients and connections safely when Lambda reuses an execution environment. Then measure the actual user impact. If a latency-sensitive path still needs more predictable startup time, evaluate provisioned concurrency. For supported runtimes and use cases, evaluate other AWS startup performance features as well. Avoid treating scheduled warm-up invocations as a guarantee. Lambda can recycle execution environments, so warm-up events are not a replacement for intentional latency design. The fastest way to learn the difference is to build the same tiny endpoint twice. In EC2, you launch a virtual machine, connect to it, install a web server, and from that point on, you are responsible for the operating system. In Lambda, you upload a handler and wire an API trigger, and AWS owns the server underneath. The point is not which one is easier on paper. It is which operating model you are actually willing to own. Build both once this week, and the decision stops being theoretical. What actually causes a Lambda cold start? Lambda needs a new execution environment. It downloads or loads the function code, starts the runtime, runs initialization code outside the handler, and then invokes the handler. A later request may reuse a warm environment and skip much of that initialization. But reuse is not guaranteed, and new environments can also be created when traffic grows. In production, EC2 and Lambda rarely exist alone. CloudWatch provides logs and metrics. API Gateway can route HTTP requests to Lambda. S3 can invoke a function when an object arrives. DynamoDB or another data store holds durable state after a function finishes. When a workload does not fit Lambda's execution model, you might evaluate ECS, Fargate, EC2, AWS, Batch, or another compute service. The answer depends on the duration, traffic pattern, control requirements, and operational model, not on a single hard limit alone. A common beginner mistake is treating Lambda's temporary environment like a persistent server disk. Lambda can reuse an execution environment. When that happens, data in memory or files in Dachengchow MP may still be present. But that reuse is not guaranteed. Another invocation can run in a different environment, and Lambda can recycle the old one at any time. Use local memory and temporary files only as an optimization or cache. If data must survive, be shared, or remain correct across invocations, store it in a durable external service such as S3, DynamoDB, a database, or another appropriate data store. Follow a common serverless request path. The browser loads the front end from CloudFront and S3. Then API Gateway receives the API call and invokes your Lambda function. Lambda reads or writes data in DynamoDB, then sends the response back through the same path. The Lambda step is the place where a cold start can add its delay. For your first Lambda test, know the shape of a minimal Python handler. A common handler receives two arguments, event and context. The event contains information from the service that triggered the function. The context contains runtime information, such as the function name, remaining execution time, and request metadata. For common API Gateway proxy integrations, the handler returns a response object with a status code, headers when needed, and a body. API Gateway uses that object to build the HTTP response. The exact event and response shape depends on the trigger and integration, so always check the current documentation for the service you are connecting. Quick recall from the handler you just saw. In a minimal Python Lambda handler, what two arguments does the function receive? Event and context. The event tells you what happened. The context tells you about the current execution environment and invocation. Here is your lab for this week. Before launching anything, create a small AWS budget and a billing alert. Treat alerts as early warnings, not guaranteed shutoff switches, and check the current pricing of every supporting service you add. Then pick one tiny non-critical task, such as a simple API endpoint. Build it twice, once as a Lambda function behind API Gateway, and once on a small EC2 instance. When both work, inspect CloudWatch logs and compare the experience. What did you configure? What did you operate? What did you pay for while idle? What information was available when something failed? That comparison will teach you more about EC2 and Lambda than a dozen diagrams. When CLF-CZO2 presents a scenario, read the trigger words carefully. Image processing after an S3 upload points to Lambda. A long-running process or a workload that needs deep operating system control points to EC2. The trap is thinking that serverless is automatically the right answer for every question. It is not. The exam is testing whether you can match the workload's shape to the right compute model. Before you deploy anything for real, add 5 guardrails. First, create a budget and billing alert so unexpected usage is visible early. Second, use environment variables for non-sensitive configuration, such as a bucket name, feature flag, or log level. Store credentials, API keys, tokens, and database secrets in AWS, Secrets Manager, or another managed secret store, not in code or ordinary configuration. Third, keep function dependencies and initialization work focused. Smaller, simpler functions are easier to deploy, observe, and tune. Fourth, send useful logs and metrics to CloudWatch so you can troubleshoot failures. Fifth, give each EC2 workload or Lambda function only the IAM permissions it genuinely needs. Least privilege is not an advanced feature. It is the default design goal. The real shift is not memorizing service names. It is learning to classify the workload before choosing the service. Instead of starting with, which AWS product should I use? Start with the work. Is it short and event-driven? Does it need a persistent process? Does it require operating system control? What happens at idle? How will it scale? Where will you see failures? What will the complete architecture cost? Experienced engineers do not assume Lambda scales every application problem, and they do not assume EC2 is the safe default. They match the execution model to the workload, then use logs, metrics, IAM, and cost controls to operate it responsibly. That decision mindset is the skill this lesson and the exam is trying to build. One final checkpoint. You have two resources, a running EC2 instance and a standard on-demand Lambda function with no invocations. Both receive no work for the entire weekend. Which one continues to incur compute charges simply because it remains running? The EC2 instance. A running EC2 instance remains allocated and continues to incur its applicable compute charges even when the CPU is mostly idle. What about the standard on-demand Lambda function? If nothing invokes it, there is no request or execution duration charge for the function. But remember, that doesn't mean the entire serverless architecture costs zero. Provisioned concurrency and supporting services can still generate charges. So the lesson isn't, Lambda is free when idle. It's, the standard on-demand Lambda billing model follows invocations and execution rather than keeping a general-purpose VM allocated while it waits for work. That's one of the fundamental economic differences between these two compute models. Let's finish with 3 things I want you to remember. Number 1. EC2 gives you a virtual machine. You choose the operating system and instance type. You control the host environment. You can run persistent processes. And you're responsible for more of the operating system, patching, monitoring, and administration. While that EC2 instance is running, you pay for its applicable compute time, even when the workload is mostly idle. Number 2, Lambda gives you event-driven compute. You provide focused code. An event invokes it. AWS manages the underlying execution environment. A standard on-demand Lambda function bills primarily by requests and execution duration. But one standard invocation currently has a maximum execution duration of 15 minutes, and you don't receive direct host access. Number 3, choose from the workload, not the service name. Ask, is the work event-driven or continuous? How long does it run? Does it need operating system control? Does the compute need to maintain a persistent process or connection? Where does durable state live? How does it scale? How will I troubleshoot it? And what will the complete architecture cost? Sometimes the answer is EC2, sometimes it's Lambda, sometimes it's both, and sometimes the correct answer is neither. A container platform, AWS batch, or another compute service may better match the workload. That's the real cloud architecture skill. Don't force the workload into the service. Match the service to the workload. Now don't stop at the diagram. Build the same tiny application twice. Deploy one version on EC2. Deploy another using Lambda. Compare what you configured. Compare what you operated. Compare how you debugged each version. Compare what happened when the workload was idle. And document why you would choose one architecture over the other. That's how you turn certification knowledge into a portfolio project. And in the next video, we'll add another compute model to the decision: containers. We'll compare ECS, EKS, and Fargate so you understand where containers fit between virtual machines and serverless functions. Remember, careers aren't built by watching videos. They're built by applying what you learn. Build it, break it, troubleshoot it, document it. Thanks for watching. Hired in IT, where we're turning IT knowledge into career opportunities. Next up, the container decision. Part 6 compares ECS, EKS, and Fargate, so you know when serverless containers beat both EC2 and Lambda. EC2 is the server you keep, Lambda is the function that appears for an event, and containers sit right between them. The exam will make you choose, Click through to that next video and we'll sort it out. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.